Yeah. So last time we started a bit of Diels-Alder, but we didn't really get to any problems or anything. So we're just going to pick up from there. And since we are on Zoom, I can have you guys just annotate what you think the answer is, which is a lot easier than the whiteboard situation, I think. So there's a bunch of these Diels-Alder reactions. I am going to ask, yes, I am posting this recording. I'm going to ask if, I guess, one of you to do a problem. So, volunteers.
I can try.
Okay, please do try.
Okay, so
You starting with the first one?
yeah. So I was thinking go from here to here. And then you make her cyclic. This is really bad.
No, that's actually pretty good for like a mouse drawing.
The only part that I get stuck on is the stereochemistry of it, but
Like whether it's up or down.
yeah, and then like yeah. So
Okay.
that's what I got.
So the top aldehyde is up and the bottom aldehyde is down.
Yeah, like a transformation.
Yeah, that's perfect. So this drawn as a chair would look something like this. Okay, that's good. Your arrows and everything are perfect. Okay, that's terrible. This entire section gets pushed up as a bridgehead, and then you just combine it with the new bonds like this with the diuniphile. So we do that. And then how do you know if the diuniphile substituents are pointing up or down?
If it's inward or outward.
Yeah, if it's facing inward or outward. So the top aldehyde, this one is facing which direction?
Outward.
Yeah, it's outward. So it's going to be facing up in the final product, right?
Facing up like the,
wedged.
oh, wedged. Okay, okay.
Just like that.
Okay.
And then the bottom one is facing left, closer to the diene. Since it's facing in that orientation, it's going to be pointing down in the final product.
Okay.
So do you guys think that there's going to be an exo and endo product for this? There isn't, because the diuniphile is trans. So when you add it, the substituents are also trans, meaning you can't get the exo cis or the endo trans configuration. It's all just one product. So yeah, perfect. Anyone want to try the second one? You wouldn't rotate. Okay, yeah, Madison, go ahead and do it. So you wouldn't rotate the single bond to make it cis. Do you mean this single bond in the final product? Oh, like these up here? So those are sp2 hybridized bonds. They don't have free rotation. If we had like this, then it could rotate around this bond, but when you have an alkene, the substituents attached to it are locked in that position.
So
And Madison is right. There's no reaction in the second one. There's no reaction because the diene has to be S-cis to react in Diels-Alder. This is S-trans, and S-trans just doesn't react. And since it's in a ring, it can't rotate from S-trans to S-cis. Okay, so the third one. Okay, if no one wants to do it, that's fine. Okay, thank you. So I think you hover over the top and then you'll see a little pencil with annotate under it, and you're just gonna click on that. Okay, did you figure out the annotation?
Yeah, I did. I'm just having trouble how to work it out. Hold on. Yeah, I don't want to take off too much time. Just go ahead and do it yourself.
Okay,
Oh,
okay, no problem. So for this one, we do the exact same 3-arrow mechanism for each Diels-Alder reaction. So I'm gonna redraw this so it's just easier to like visualize. But I like to have the diene and dienophile like facing each other in the right configuration, just like this. So you have the diene, you have the dienophile, and now you just draw the arrows of the attack. So the first one goes from top of diene to top of dienophile, bottom of dienophile to bottom of the diene, and then this alkene just resonates up here. So your final product is going to look like this. You have a new alkene up here, you have a new bond over here, and a new bond over here. And then this is just going to be where we attack the dienophile. And then the dienophile is an alkyne. So what's it going to look like in the final product after the reaction? It's going to be a double bond. So you have a double bond, and then you have your ketones. And there's no exo or endo product in this case because there's no substituents facing up. The whole thing is kind of just planar. And because this was an alkyne, this is a double bond, and these carbonyls are planar. Okay. So there's a few more. Would you guys want to do them, or should I just go ahead?
Can I try the first one?
Yes, please.
So I did. This is really bad. Oh my God.
That's fine.
And then, would this be dashed CL?
It's facing outwards, right?
Yeah.
So is that dashed or wedged?
Wedged, I guess, right?
Yeah, it would be wedged.
Okay. And then this is like so. Oh my God. Like that.
Yeah, so both of them are going to be dashed, wedged. Yeah, they're both
They're
facing
both
up. That's
wedged? Oh.
perfect.
I
Yeah,
thought that one was
because they're
planar.
both. No, that's the planar thing only happens if you have an alkene in the middle. So if you have a dienophile that's an alkyne.
Okay.
But that's right. Oh, okay, people want me to go back up for a second. So, wait, I'm sorry, I'm gonna erase your beautiful drawing. So in the second reaction, are you talking about this one with the square?
I was talking about the one on the second page.
Oh, okay. Yeah, you're right. Let me try the product out for the first one. Yeah, you could rotate them. That would give you an endo product. So for all of these, like this is the technically correct product for the orientation of these reagents, but the major product is going to be endo anyways. So based on like this specific given reaction, like you would get this exo product, but always the major product is going to be endo. Yeah, this second reaction is no reaction because this diene is not conjugated. And if it's not conjugated, you can't react it. Okay, we just have one more, but I think we've like done a lot of these, so we could just move on to save time. Okay, so now there's multiple choice. I think this is kind of similar to what you'll see on the exam. You'll see a lot of like dienes and dienophiles, and you'll have to just mostly find which one is going to be more reactive. So what do you think the answer to this would be? It would be C. Why would that react the slowest?
I just thought because it had 2 electron withdrawing groups on it.
Yeah, but remember for a dienophile, we want electron withdrawing groups on it. The EWGs only
okay.
slow down. Yeah,
So
they
then
only
D.
slow it down. It would be D. It slows down an electrophilic aromatic substitution, but for Diels-Alder, it speeds things up. So D has electron donating groups, the ether and the isopropyl, which makes the dienophile much worse. And then the rest of them all have electron withdrawing groups on them, so they would react pretty quickly.
So you would say the more electron withdrawing groups or electron donating groups, I mean, is going to be the slowest.
For the dienophile, yes.
Dienophile.
But for the diene, the more electron donating groups, the faster it is. Okay. So this is retrosynthesis, but it's multiple choice, so it's much easier. So what do you think it would be? Yeah, I'll post answers. So we think C. Yeah, that's right. That's the only possible combination that would give this product. In the first one, you don't have a diene. The second one would give you some crazy bridged molecule. And then D would also give you a crazy bridged molecule. So yeah, let's see. Okay, another one. Okay, so A. We all agree with A. Yeah, it's A. So you can tell because of the bridgehead, this is the only thing that would give you that bridgehead. And you can tell because of this alkene. So you know you started with an alkyne. And then the rest of them, like, yeah, they just wouldn't work. Okay, this problem I threw in just for fun. It's kind of ridiculous and I don't think you're gonna have to do it. So we're just gonna skip that. I'll post the answer to it later. Okay, so chapter 14. Chapter 14 is going to be mostly IUPAC, and then also he's going to give you a list of like cyclic molecules and then ask you which one is aromatic. So that's the important stuff for this chapter. But on a benzene, there's 3 important positions, ortho, meta, and para. So this is asking to label those relative to the methyl. The ortho position is 1 carbon away from the substituent that you're looking at. So that would be this one. Meta is 2 carbons away. So this one, and then para is on the opposite side. So there. And then that's just important for like everything in this chapter, but mostly for naming. For naming, I posted a link to a bunch of benzene derivatives. So like, for example, it would tell you like what a toluene looks like or what the name for a benzene with an amine on it is. I think it's really helpful, especially for IUPAC. But it's mostly multiple choice like this. So this is asking which molecule is 4-chloro-2-nitroaniline. Okay, we all agree with B. All right, just gonna go with B. That's right. So with these, you just have to find the benzene skeleton that you're looking at, and you find that by the very last suffix. So we're looking at aniline. Aniline is a benzene with an NH2 on it. So that means we start counting number 1 from where the NH2 is. So this carbon is number 1, and then we count the rest of the substituents going from the NH2. So this group, the NO2, is called nitro, and that's on carbon 2. This group is a chloro, and it's on carbon 4. So that works, right? 4-chloro-2-nitro. It's gonna be like so I'm posting it, it's gonna be in Canvas, and then the answers are also gonna be in Canvas. Okay, so now it's asking you to draw 3-amino 4-chloro-benzaldehyde. So we start by finding the benzene skeleton, which is benzaldehyde. This one's straightforward, it's just a benzene with an aldehyde on it. So I'll just put it here. And then we have 3-amino and 4-chloro. So we count 3 carbons. So the amino goes here, which is in NH2, and 4-chloro, 1, 2, and 4. Okay. So now is aromaticity, which I think is the bulk of the chapter 14 questions. So rank all of these in decreasing order of stability.
Anti-aromatic is least, and then non-aromatic, and then aromatic.
Yeah, perfect. Although I think Dr. Roche is not concerned with not aromatic and anti-aromatic. I think he's mostly concerned with identifying what's aromatic. So down here, I just typed out all the criteria and rules for aromaticity just to save time. And yeah, that's just part of the worksheet. But I didn't type the criteria for a molecule to be not aromatic. So what does it take for a molecule to be not aromatic?
To break any of the rules like cyclic, planar, fully conjugated.
Yeah. Some easy ways to spot non-aromatic is an odd number of radicals. And like an sp3 atom. Okay, and then I also went ahead and typed out all of the heteroatom rules, like all the weird things, like how it can choose and all that. But I'm pretty sure Dr. Roche is not concerned with that. So I don't think there's going to be much of it, if any of it, on your exam. I think it's going to be pretty straightforward, just like counting 4n plus 2. Okay, so now we have a bunch of molecules, and all you have to do is find the ones that are aromatic. So I'll give you guys like a minute to do that. Yeah, boron has to be always sp2. It can't choose to be sp3. Yeah, I think the rest of the heteroatoms can choose between sp2 and sp3. Okay. Did you all finish with that? Okay. Could someone just go ahead and like underline the ones that are aromatic? Okay, I think it's mostly good, but I think there's one missing, and then a couple that are not aromatic. So yeah, so these two up here, in this heptane, you have an sp3 carbon up here because it has 2 hydrogens attached to it. That is going to break the conjugation and it's no longer aromatic. For the other one right next to it, you have a, oh, I just ruined. Okay. You have an odd number of radicals. You just have one radical. I know it's like kind of tiny and hard to see, but that's going to give you an odd number of pi electrons. And remember, you need 4n plus 2 pi electrons. If it's an odd number, that's impossible. So this is also not aromatic. The rest of them are correct because they have 4n plus 2 pi electrons. They're all cyclic and planar, but there's one missing. This one is going to be aromatic. It's just like pyridine. So the oxygen is a part of the pi bond here and it contributes 1 pi electron. So there's a total of 6 pi electrons in the system. Okay. If there's no, are there any questions or you want to move on to chapter 15?
I had a question on the last one. If I don't see like the double bonds inside the ring, so that means it also still can be aromatic though, because because conjugation, I guess. I'm just stuck on the last
You mean
one.
for this one?
Yeah.
Oh, right. So it is conjugated because it's all sp2 and you
Oh.
have these radicals.
Okay.
So
Okay.
all of these carbons are sp2. An even number of radicals. Yeah, an even number of radicals might be aromatic, but you have to count and make sure it's 4n plus 2 still. So in this case, there's 2 total pi electrons, which is a 4n plus 2 number. So it's all good. Okay, chapter 15. Oh, wait, real quick, before chapter 15, there was one thing I wanted to include. So way up here for the 1214 edition, there's one more thing you should know. For kinetic, if it's asking for like a kinetic major product, that's going to happen when the reaction is not at equilibrium. So in the question, it's going to say like, this reaction was like performed or was ran not at equilibrium, or it was performed under equilibrium. If it's not at equilibrium, then the kinetic product is the major one. If it was run under equilibrium, then the thermodynamic product is the major one. And then that'll be up there when I upload the answer key. Okay, so back to 15. So compared to other conjugated systems, benzene is more or less reactive. Yes, it's less reactive because it's more stable. The more stable it is, the less it's going to want to react and disrupt its stability. So because of that, what do we have to use to encourage a reaction?
A catalyst.
Yeah, we have to use a Lewis acid catalyst. The Lewis acid catalyst is there to make the electrophile super electrophilic. It's going to make it strong enough that it attacks the benzene. And then when a benzene does undergo a reaction, does it undergo an addition? Yeah, it goes through a substitution. And a substitution is an addition plus an elimination. So because you have those two steps of addition and elimination, there's going to be a bunch of steps in a total electrophilic aromatic substitution reaction. So step one, you're going to need to react the electrophile with a catalyst to make the electrophile stronger. After you do that, the electrophile is strong enough to attack the benzene and break aromaticity. So in step two, the electrophile or the electrophilic species attacks the benzene and forms the iridium ion. So in this step, aromaticity is lost. And then in the third step, you have to restore aromaticity because it doesn't like being non-aromatic. So in step three, you do an elimination reaction and you get an aromatic molecule back. So from those three steps, the mechanism just looks like this. So the first step is that you have to react your reagents together to get a super strong electrophile. So the Br2 on its own is not electrophilic enough to do an attack. So you combine the Br2 with FeBr3 to get your electrophilic species. So that's going to look like this.
Aló. Tá bom, me dá
So now this is electrophilic enough that the benzene can attack. So the benzene just goes in and attacks this bromine and kicks off the rest. And then you get this intermediate step called the iridium ion. And then the third step is just the elimination reaction. So the conjugate base, the Br minus, goes up, steals the hydrogen, and then those electrons go back in to reform the double bond. And then you end with a bromobenzene. There might be some like word problems on that. So he'd be like, I don't know, like what happens to the uranium ion after the electrophilic species has been added. Okay. So now you have this table of reactions. I just filled a little bit out. It's kind of annoying to go through everything, but might as well. So for the first reaction, nitration, what reagents are we using? Very close. So it's not NO2 over H2SO4.
HNO3.
It's HNO3. Oh, what? And then the electrophilic species that forms after this reacts with each other is called a nitronium ion, and it's just NO2 plus. I used to get questions like this that was like, in a nitration of benzene, like what is the electrophilic species? And it would be nitronium ion. Okay, for sulfonation, what do we use? Yeah, we use SO3 over H2SO4. The electrophilic species for this is an SO3H. Okay, and then for halogenation, if you're halogenating with chlorine and bromine, then the reagents are X2 over FeX3, but this is only for chlorine and bromine. If you want to add an iodine onto the benzene, it's going to be slightly different. So for iodine, you use I2 over HNO3 or H2SO4, any Bronsted acid basically. For the top one, the X2 over FeX3, the electrophilic species is this complex that we saw earlier. And then for the iodine, the electrophilic species is just I plus, but I don't think you need to know that. Okay, and then the last two are going to be Friedel-Crafts. So you can have Friedel-Crafts alkylation and then FC acylation. So for alkylation, what reagents are we going to use? Yeah, so for Friedel-Crafts, one possible set of reagents, or the most common set of reagents, is an alkyl halide over a Lewis acid, usually AlCl3. We'll just start here because there's 3 different reagents we can use. So the first one, Rx over AlCl3. The whole point of Friedel-Crafts, or the reagents you use for Friedel-Crafts alkylation, is to create a carbocation. So the electrophilic species is an R plus carbocation. And then there's 3 methods you can take to get that. So the first one is the Rx over AlCl3. The second one, you could use an alkene and then a Bronsted acid, usually HF. So in this case, if you're using an alkene, it would look like this. The alkene attacks the HF, and it's a Markovnikov addition. So you get the carbocation on the most substituted side. And then you have your electrophilic species right here. The third one is with an alcohol and BF3. So you start with ROH, and then you react it with BF3. And this is also, the OH basically attaches to the BF3, and then it pops off and you get a carbocation. So with all of these, they're just different ways to get a carbocation. So you just chop off the alkene, and you add a carbocation, and you chop off the alcohol, add a cation, and then stick it onto the benzene. Okay, and then for acylation, what reagents do we use? Yeah, the alcohol makes itself a leaving group. Okay, so that's right. It's a X or a halogen attached to a carbonyl over AlCl3. Technically, it's called an acyl halide. So, yeah. So an acyl group is basically just this. If we add a halogen to it, this is called an acyl halide. And then that goes over a Lewis acid catalyst. In this case, the electrophilic species is called the acylium ion, which, once again, we just take the halogen, react it with AlCl3, chop it off, and replace it with a cation. So the electrophilic species looks like this. So there's two resonance forms, but it's not going to attack to the oxygen because the oxygen is more stable than the carbon. The carbon is more unstable, it's more reactive. So when you do a substitution with it, you just attach the benzene right to this carbon. Okay, and then there's some exceptions for Friedel-Crafts, or things you have to watch out for. So there's two kinds of groups that are going to prevent a Friedel-Crafts reaction from happening. So what are those two? The triple bond oxygen is called an acylium ion. Yeah, so it's not going to react if you have an amine or a strong EWG. So out of all of these benzenes, which one is able to do a Friedel-Crafts? Yeah, F can do it because bromine is not a strong withdrawing group. D can also do it because this is an ester, but technically, since it's attached to the oxygen, it's yeah, it's gonna work like an ether. It's gonna count as an OR substituent. And then that's gonna be activating. Because you have these lone pairs that go in and increase electron density. Okay, speaking of activators, we have this thing. So activators are going to be electron donating groups that make the benzene more reactive and they increase the reaction rate. And then this is the resonance reasoning behind that. So when the EDG donates electrons in via resonance, you can see that there's a lone pair, and the lone pair gets placed on the ortho and para positions, these 3 carbons. So overall, you have those 3 carbons as a delta negative. The delta negative makes them more reactive in an electrophilic substitution. And then this is a question I think is in his test bank. He's going to give you like a benzene with a certain group on it and ask which carbons are delta negative or delta positive. So delta negative makes those carbons more reactive, and that's why they're ortho-para directors. So here's this massive explanation for why that is. So the lone pair lands on the ortho-para positions. That makes them more electron dense. So activators overall increase electron density and activate the benzene. The most electron dense carbons are in the ortho and para positions, so activators are ortho-para directors. So now for deactivators, we can see that the resonance arrows are going the opposite way. They're going out of the benzene. So deactivators are electron withdrawing groups that make benzene less reactive. Electrons drawn with a half arrow. But this is a full arrow. Okay, so it makes the benzene less reactive, which decreases the reaction rate. And overall, those 3 carbons are going to have a delta positive charge this time. The delta positive makes them much less reactive, so you don't really want to add a new group onto there. So the positive charge lands on the ortho-para positions. That makes them less electron dense. So deactivators decrease overall electron density and deactivate the benzene. And then the most electron dense carbons in the benzene are now in the meta position. So deactivators are usually meta directors, except for halogens. So here's this table with all or most of the activating, deactivating groups, and then where they direct to. So there's only one thing in ortho-para deactivators, which is halogens. Something to note about halogens, they're weak deactivators, and they're EWGs by induction. So it's going to be a para major product. So it is donating electron density to the ortho-para positions. They are delta negative, but because a halogen withdraws electron density, the ortho carbons are also slightly delta positive. So it kind of just cancels out and you would get a para major. And then another thing to note is that if you have an R group on a benzene, it's going to be an ortho major product because it's by induction. So the closer you are to the R group, the more reactive it is. And then this last category, the deactivating groups that are meta-directors. These are the groups that you can't do a Friedel-Crafts reaction with. So if you have a benzene that has any of these on it, you're not going to be able to do Friedel-Crafts. All right, so we're good to move on to practice problems for 15. Okay, so the first one, it's asking for the benzene that will be the most reactive. So which one would it be? Okay, so 3 would be pretty reactive because it has 2 R groups and then R groups are activating. But there's one that has a better activating group on it. Yeah, 4 has the amide. So one thing to note, an amide is different from an amine. So this is an amide when it's attached to a carbonyl like this. If we just had a plain NH2, that's an amine and that's the most reactive. This NH2 is a weak or a moderately good activator because it has this lone pair and it sends that lone pair in to do resonance. Because it's a resonance activator, that's much stronger than just an induction activator. So that's going to be more reactive than just 2 R groups. Isn't the lone pair? Yeah, so the lone pair of the amide can go both directions. You can send it up to the carbonyl or you could send it into the benzene. So it's still activating, it still increases electron density, but not as much as an NH2 for that reason. So the resonance activator is stronger than just the induction. I don't think it would be weaker because it's still resonance. And I think that would be more powerful than the induction. And you also have this R group over here. Okay, so the next one is asking the NH. Oh, you mean NH like the amide? So it's right here on the chart. So it's after like your amine and your ester and alcohol. Yeah, for this chapter, like you could just reference the chart for the whole thing. Okay, So now, which of these 5 is going to be the least reactive? The NH2 ones, yeah, cannot. But the NH, the amide can, because it's weaker. Four would be the least reactive. Yes, because 4 is the only one with a strong deactivator on it. Number 1 has an R group, which is an activator. Number 2 counts as an OR, but weaker than an OR because it's an ester. It's still activating though because of resonance. And then the NH2 is a very strong activator. And then 5 is a weak deactivator. It's not as strong as this carbonyl is going to be. Okay, now we have a bunch of reactions. Do you guys want to do them or do you want me to just run through them? It's up to you. Okay, I'll do that. So for the first one, this is an interesting reaction. So there's 2 steps. So step 1, you take this benzoic acid and react it with Sokol 2. So what do you think that's gonna, like, what do you think happens with that? Yeah, so the Sokol 2 is a protecting group from chapter 11, and it replaces an alcohol with a Cl. So it does attach, and then it kicks off the OH. So now we have a molecule that's a carbonyl with the halogen attached to it. Do you remember the special name for that? Yeah, it's an acyl halide. And then what's the role of an acyl halide in our Friedel-Crafts acylation? Yes, an acyl halide is the electrophile, and then it gets, after reacting with a catalyst, it turns into an acylium ion. So yes, perfect. So in step 1, we made an acyl halide. So we made an electrophile. Now we take that acyl halide and we're reacting it with benzene and AlCl3. So I'm going to write it like this. So we have an acyl halide, a benzene, and a Lewis acid catalyst. What do you think happens? Yeah, an acylation. So basically when you have an acyl halide and a Lewis acid catalyst, you know that they're going to react with each other, and the halide, the halogen from the acyl halide gets chopped off and turned into a cation. So after these two react, you get your acylium ion. And then now what can we do? Yep, we just attach the benzene. So I just draw a bond from anywhere on the benzene. There's no substituents, so we can attach it anywhere. I just like draw a bond right to the carbocation, and then that's your answer. So the reagents were all were out of order, but we still got all the reagents necessary for a Friedel-Crafts acylation. The name of this compound, diphenylketone, I don't know. Oh, it's called benzophenone. Oh no, technically the IUPAC name is diphenylmethanone. Okay, that makes sense. I think that's chapter 16. Yeah. Okay, so the next one, we have these reagents. So what do we know we're gonna add to the benzene? An NO2, we're gonna add a nitro group. But where are we gonna add the nitro group? We have to look at the directing effects on the benzene. So there are two directors. We have this top carboxylic acid and then this bottom methyl. So where does the top one direct to? Yeah, it's directing meta, because that's a deactivator. So it's directing to these two carbons. And then where is the methyl directing? It's directing ortho. So also those two carbons. So that is very convenient. Both directors line up, so you're gonna get one product. Yeah, so it's not para because of the carbonyl, and it's also not para because the R group is an induction donor. So induction, the further away you get from the R group, the less electron density you get. So the ortho positions are always ideal for an R group. So it's mostly an ortho director. So our new group gets added here, and it's just one product because of symmetry. Yes, still ortho para, but major ortho, yeah. And then if you have like substituents with competing directing effects, you choose to prioritize the most reactive one. So I'm going to see if there's examples that are like that. Okay, so for this one, we have the funky reagents. Do you remember what these reagents, like what reaction they're part of? Yeah, they're Friedel-Crafts alkylation. The way this works for Friedel-Crafts alkylation, you use the alkene, attack the HF, and you get a carbocation on the most stable position. So after that reacts, you get this carbocation. And then you literally just go ahead and stick it onto the benzene. So for the next one, we have two benzenes. And well, first, which reaction is this?
An R group to a halogenation, or yeah, halogen.
Halogenation,
I meant like the R group to halogen, not halogenation.
R group to oh, like
R to X.
group to halogenation. Yeah, so an alkylation, right?
Yeah, sorry.
Yeah, it's gonna be an alkylation. So now which side of this molecule do we attach it to? You have benzene A and benzene B. So which benzene do you think it would go on? I think it would go on B. So remember, a limitation of Friedel-Crafts is that you can't add to a benzene that has a strong deactivator on it. This carbonyl is a strong deactivator, so it's going to deactivate this entire benzene. So we can't do a Friedel-Crafts on that side. So when I see stuff like this, I just kind of go ahead and chop it down the middle. And I see that, okay, the left side has a ketone or a carbonyl attached to it. And then the right side just has the amide. So the right side is being activated by the amide. So we can only add it there. So where is the amide directing to? Which carbons? It's going to direct orthopara. But which product do you think would be more ideal? Like considering steric hindrance. Para, yeah. It is a methyl, so it's not too bulky, but I still think para would be favored because you have this nitrogen and that massive carbonyl spinning around. The HF one is alkylation. So it's probably para major, but I'm sure you get ortho product as well. Okay, so the next one, same idea. So which reaction are we doing here?
Acylation.
Yeah, it's an acylation and it's a Friedel-Crafts. So the limitation applies to it, right? That you can't do it with a strong deactivator.
So would you do the left side?
The left side
Or,
has
I
a
mean-
strong deactivator on it.
Yeah, sorry. I just looked at the chart.
Yeah, so you would do the right side. The left side has this NO2, which is the most possible unreactive substituent to have on a benzene. And it's not even just Friedel-Crafts, like nothing likes to react with it. But you know for sure that you're going to add it to the right side. The right side has this methyl, and then this whole thing counts as an R group. So it has two R group activators on it. So which carbon do you think we're going to add the acyl group to? Actually, first, let me draw out where each R group is directing to. So R groups direct ortho. So this one is directing here and here. Then the other one is directing to those carbons. So from carbons 1, 2, and 3, which one do you think the acyl group is going to get onto? Yeah, it's going to stick itself on carbon 2 because that has the least steric hindrance. An acyl group is pretty bulky, so you want it to be the least sterically hindered. Okay, the next one. From the reagents, which reaction are we doing? We're doing halogenation, and we're going to add a bromine. So now we have to look at the directing effects and see where the bromine is going to get added. So this NO2 group is what kind of director? It's a meta director. So it's going to direct to this carbon, not this carbon because it's already occupied. And then what about the ketone? Ketone is also meta. So that would also be this carbon. Once again, it conveniently lines up. So there's only one real spot that we're going to add the bromine to. All right, this next one. So we have an alcohol and a BF3. What reaction do we think that is? Oh, if the ketone would be para to the nitro. So we do the same thing, we just draw out their directing effects. So the NO2 directs meta, so down here. The ketone also directs meta, which is up here. So if this situation happens where they're not directing to the same carbon, you look at which substituent is more reactive. So you just scroll up to the chart over here, and it gives you the order of reactivity from most to least. So we're comparing the nitro and the ketone. So the nitro is all the way down here at least reactive, and then the ketone is up here. It's still pretty bad, but more reactive than the nitro. So because it's further left on the chart, it's more reactive. We know that the ketone has priority. So the carbons that the ketone directs to are going to be the major product.
So if it's more reactive, would it be a stronger, if it was more reactive, would it be a stronger deactivator? Like on the
More
chart?
reactive is weaker deactivator. Yeah, the more reactive it is, the further to the left it is, the weaker deactivator.
Okay, okay, I see the trend now.
Okay, so now the next one. Yeah, the stronger director is more to the left. So for this reaction, we have an alcohol and BF3 overheat. So what reaction is that?
Alkylation?
Yeah, it's alkylation. And then remember, if you have an alcohol and BF3, you just know chop off the alcohol and put a carbocation on there. Once you have a carbocation, you know you just slap it onto the benzene. But where are we gonna put it on the benzene? Where is the sulfur directing to? The sulfur is a resonance donor, so it directs orthopara. But what do you think it's going to prefer, ortho or para?
Would it be para because it's steric hindrance?
It would be para because this like whole situation is pretty bulky and it's going to interfere a lot with the R group attached to the sulfur. Okay, it's really janky. All right, I think this is okay, almost the last one. So what reaction do you think this is?
Another alkylation?
It's another alkylation. And then what do you think the product is going to be? It would not occur. You're right. So this nitrile group is part of the strong meta deactivators. That means you don't really do Friedel-Crafts with it. I mean, I'm sure you'd get like a tiny bit of yield, but basically no reaction.
Would it be safe to say if we don't see it in the activator chart or deactivator chart, it's pretty much no reaction?
It is on the activator chart.
The triple bond nitrogen?
Yeah, that's CN.
Oh, geez. Okay.
And then maybe I should have written out the triple bond, but it's also up here.
Okay, thank you.
Just for Friedel-Crafts. I mean, the rest would also be like terrible yield, but it would occur more than Friedel-Crafts. Okay, the last two, these are not on the worksheet. I just added them because I went through your quiz and I saw that I haven't done anything like this, so I might as well just do some. But the first one is interesting because it's intramolecular. So in step one, we have Sokol again. So what's that gonna give us?
A protecting group?
Yeah, we just get an acyl halide. That's right. So intermediate A. Would be this acyl halide. And then now what are we reacting it with?
Would the chlorine be taken off and there be a carbocation?
When you put an acyl halide with an AlCl3, it chops off the chlorine and you get the acylium ion. So now you have this as an intermediate. But now what? There is no other benzene in this reagent line that we are going to react this with.
Would it react with itself?
It would react with itself. So you would literally just bring this whole thing around and stick itself on the benzene. And which position do you think it would add?
Ortho?
It would add ortho, because this counts as an R group. It's R group, so ortho director. So we're just going to draw this going all the way back to an ortho position. Oh, and I'm going to number the carbons just like for sanity. Is that right? Okay, so we have carbon 1, 2, 3, and 4. Yeah, that's right. And then you have the methyl sticking out on carbon 2. So like this. So that's your final product. I think it could also react with like another molecule of itself, like this. But I think Dr. Roche wants you to like think and then make it react with intramolecularly. Okay, and then the very last one, we have one of these. So this is like a popular question about the uranium ion intermediate. And it's giving you a bunch of resonance structures when the intermediate forms. That would be when you have that sp3 hybridized carbon before you do the elimination step. So you have a carbocation that's being stabilized like this. And then the carbocation is just like delocalized around those conjugated carbons. So it can be in any of these 3 or 5 positions. It can be in here, here, or there. So knowing that those are the possible positions for the carbocation, what do you think that eliminates from the answer choices?
It eliminates the last one.
Yes. Also on the last one, you don't have this sp3 hybridized carbon. That is important. And then from that principle, we can also eliminate 2, right?
Yeah.
Because it's not the correct hybrid. So now from 1, 3, and 4, what do you think is the most stable position for a positive charge?
3 because it's tertiary.
3 because it's tertiary. And it's also the closest to the CH3, which is an induction donating group. So it's a positive charge, which means it wants electron density. And the CH3 is an induction donor. So it's donating electron density to the electron deficient carbon. So yeah, that's the most stable position. We are done early, so that's cool. I will stick around though if any of you have questions or anything you want to clarify. Scroll up how far? Do I have access to the last homework review? Like the exam 2 review that he sent out? Yes, I do. Was there anything you wanted to do from this? There's a few multi-step, aren't there? The 13 and 14 one, this one? Okay. Yeah, I can do this. And then after that, I'll do the hard Diels-Alder. So let me just erase all of this. Then we'll start fresh. So this is a retrosynthesis. So I kind of just looked at what was added onto the benzene. And I was like, cool, there's 2 things on the benzene. And there's also like just 2 or 3 steps. So I tried starting from a plain benzene and kind of trial and erroring it until I got something correct. So I looked at the reagents and I saw that there were basically only 2 additions, this one and this one. This is Friedel cross acylation, and then the second one is a halogenation. Since there's 2 things that you're really like adding, I'm gonna start with a plain benzene because there's only 2 substituents in the final product as well. So I'm gonna make a plain old hexagon and then do an acylation on it. So from the acylation, we know we just chop off the chlorine and then stick it onto the benzene. So product B looks like this. You get a benzaldehyde. So now that you have a benzaldehyde, we're doing a chlorination with it. So Cl2, AlCl3. And from this, we know we're going to add a chlorine somewhere. So the carbonyl is a meta director. So I'm going to add the chlorine meta to the carbonyl. Now he decided to bring back some reagents from chapter 12 and 11. So anyone remember what NABH4 does? It reduces. So the NABH4 reduces the aldehyde into a primary alcohol. Okay, on your exam and quiz, I don't think there's much of this stuff where he brings back like reagents from old chapters, but just in case, good to know what each thing does. and good to have notes on them. So NABH4 is going to turn, he likes to spice it up mostly in his lectures and homework. The exams are pretty like non-spicy. But anyways, NABH4 turns aldehyde into primary alcohol. So now we have this thing floating around. In step 2, he's giving you a strong base and an alkyl halide. So I'm pretty sure not many people remember. I definitely forgot chapter 11 at this point in the semester. But an alcohol plus strong base plus an alkyl halide is a Williamson ether synthesis. So we have this, this, and this. Those 3 ingredients mean you're doing Williamson ether synthesis. So with that, you know the strong base deprotonates the alcohol. So the NaH deprotonates the OH, you get an alkoxide. The alkoxide is now a good nucleophile. It's going to attack the ethyl iodide. So go ahead, do a backside attack, and then you get an ether. So you just get an ethyl attached to the other side. So now, is this product what we wanted up here? Are they the same thing? Yeah, so that synthesis worked. It's just a matter of knowing the reagents. And I don't think you're gonna have anything this difficult on the test. Four, 5, and 6. Yeah, do I have to leave this up for anyone? Oh, Donna, I totally agree with you. I was like trying to figure that out earlier today. I thought it wouldn't react either. So I have no answer for you. I'm sorry. I might go hunt down Dr. Roche and ask him though. So this for question 3, right? So this reaction with an anhydride and AlCl3, if you're adding this group, that's an acylation, and that would be Friedel-Crafts. But there's an amino group on here which deactivates the benzene from a Friedel-Crafts. So this problem is kind of silly because you shouldn't be able to do an acylation on that benzene. But I guess he wants you to do it anyways. So in this case on the exam, I guess if like you have multiple choice and you have an amino with a Friedel-Crafts, just go ahead and like get the theoretical answer, I guess. I honestly don't know. Maybe if you guys remember anything he said about it in lecture, or if he mentioned it in lecture at all, just follow that. Yeah, I'm gonna post answers to the packet that we just did. It's not because the methyl's on the amine, it's because the amine in general is really, really basic. Because it's basic, it's gonna react with the Lewis acid on its own, and you're not gonna have like an acylation happen. Yeah, the acid-base chemistry interferes. So I can't post answers to his study guide, I think. But this session is recorded, so you could scroll all the way to the end and take a screenshot. Wait, you wanted me to do 4, 5, and 6, right? Okay. Oh dear, it's a lot of stuff. Oh, I forgot to give you guys an anhydride question. Damn. It's okay, we'll do it now. So for this one, you're starting with a toluene and reacting it with an anhydride over AlCl3. This is an anhydride, and then when you give it AlCl3, it basically just breaks open and you get an acylium ion. So when you see this, think of this reaction. I mean, like, you don't need to care about the mechanism. Just know that it basically breaks open and one side turns into a carboxylic acid, the other side turns into an acylium ion. The way I think of it, I just like draw a line from the benzene, and then I like attack one carbonyl out of the two. So we have a methyl on the benzene, which is that directing two. It is orthopara, but ortho major. So I'm gonna draw an arrow from the ortho carbon to attacking one carbonyl of the anhydride like this. And then I'm just gonna think that this unfolds. So after that, I think product A would look like this. It would just be joined where I attacked the anhydride. Oh, not carbon counting. Okay. 1, 2, 3. And then there's an alcohol on that side. So that's product A. These reagents in this step, I don't think he's ever talked about it, but this is called a Wolff-Kishner reduction. And when you have this and a ketone, you basically just chop off the ketone and it becomes a CH2. And then that's exactly what happened here. So you see, this is just the exact same molecule, but without this ketone. So these reagents just chopped it off. And then you get this intermediate. So now that you have that, you're doing a two-step reaction with SOCL2 and then AlCl3. It's called Wolff-Kishner reduction. But now you have this thing, you're treating it with SOCL2. The SOCL2, remember, chop off the alcohol, add on a chlorine. Now you have an acyl halide. Acyl halide plus AlCl3 equals acylium ion, right? So we're gonna get this. And then what do you think is gonna happen? We're also looking at product C. So from product C, you see that it kind of just made its own ring. So you're right, it did an intramolecular attack and it attached to the benzene it's already attached to. So we're just going to draw an arrow from the acylium ion all the way to this position. And we chose that position because this is an R group and an R group is an orthodirector. And we can't attach here because there's already something. So now product B looks like this. I have to number the carbons again. Why I chose that carbon? So on the benzene, we have two directors. We have this R group and this R group. But I'm just gonna say it attaches to this R group. Well, they're both orthodirectors. So this R group over here is directing to this carbon. And also, I looked at product C and I saw that it attached to that carbon. So I just followed that. But yeah, it's orthodirecting. I guess you probably could attach it to this carbon as well and make like a weird bridge kind of thing, but that's above our pay grade. So now product B looks like this. If you have a methyl, then it's usually ortho major. I think if you have a bulkier R group, then it's more para. But in general, for R groups, it is ortho major. I guess you have to look at the sterics of each one to figure it out. Okay, but now I have this weird ketone thing. And we're giving this weird ketone thing these reagents. We're giving it NaBH4 and H2SO4 and heat. So NaBH4 reduces. So it's going to turn the ketone into a secondary alcohol. So after NaBH4, we get this. Ketone turns to alcohol. And the last step is H2SO4 and heat. H2SO4 and heat is an acid catalyzed dehydration. And that's kind of unfair to include that because if he went over it for like 1 second. And he also told me that he doesn't care about dehydration. But anyways, what acid catalyzed dehydration does, you chop off the alcohol and then you add a double bond. So yeah. When you chop off the alcohol and add a double bond, you get the final product. And the double bond went on that side because you can't like do an elimination, sorry, towards the benzene, right? Because this carbon already has 4 bonds on it. And yeah, you couldn't do another double bond like this. No, we never went over that. Okay, question 9. So in question 9, Roche added the NO2 ortho from the aldehyde. Like here or here. Oh, I didn't know he did that. I thought it would be on the meta position because the aldehyde is a meta director and it's also next to this R group, which is an ortho director. So this R group directs here. This aldehyde also directs there. So I thought that would be the answer. Okay, good. So your question is why would you choose the aldehyde over the fluorine? Yeah, so the F would be better. The fluorine it's mostly a para director. So when we think of a fluorobenzene, fluorine is the most electronegative atom like ever. So it's pulling all this electron density up away from the benzene. So by resonance, it's going to have the ortho para carbons as a delta negative. However, there's two competing forces. So by resonance, these carbons are all ortho, but by induction, they all also have a delta positive on them. And then remember, induction is stronger the closer you are to the electronegative atom. So these are also kind of delta positive. That's going to cancel out. And then like the ortho carbon is no longer activated. It's just like whatever. So the most electron dense carbon left is para. And then fluorine, that effect is the most visible because fluorine is the most electronegative. So knowing that fluorine is mostly para directing, let's look at that on this molecule. So this fluorine would direct here, this fluorine would direct there. Is that possible? No, it's not possible because there's already stuff on those carbons. So yeah, and also the strongest activating group out of everything present on the benzene is, what do you call it? These R groups. These do count as directors. So those R groups are going to be directing ortho, which is here and here. I think fluorine would direct ortho. I'm pretty sure. Yeah, we can do number one. But we're good with question 9? Okay. Oh, it might be the exception. Is that what he told you in lecture? Okay. I don't remember. Go with whatever he told you in lecture. Question 8. This one? Okay. So this is asking which set of reagents would carry out the following reaction. So in this reaction, we went from this thing to that thing plus an SO3H. And then this is just a memory thing, like you would have to reference the table of all the chapter 15 reagents, and then you'd find that this is a sulfonation reaction when you add an SO3H, and then the reagents you use for that are SO3 over H2SO4. Okay. Wait, so what else did I have to do? I had to do number one and then the Diels-Alder. I'll do the Diels-Alder first because you asked a long time ago. Okay, so this is a retrosynthesis question. It's asking you to give the diene and dienophile necessary to synthesize the product. So when I see something like this, number one, the first thing I notice is that the entire molecule is one giant ring. That gives me a major hint that the diene and dienophile were in the same molecule. Because if it wasn't in the same molecule, you'd have like bridgeheads and stuff sticking out and all of that. Because it's such a clean planar ring, I figured that I would just try it as one intramolecular reaction. So then I kind of just reversed the arrows that you draw in the mechanism. So in the mechanism, before that, I looked for hints at what could be the diene and what could be the dienophile. So I noticed that there are two electron donating groups, this OR and then this R group. This side is not very electron withdrawing, so I'm just going to ignore that. But I will consider these two EDGs as a hint. So now what do I do? So now I just kind of reverse the three arrows. So I'm going to start with this as my potential diene. That means that I take this one and I shove it back there. I take this bond on top and also bring it back down into the diene. And then there's one more arrow. I'm reversing this bond. So now I just go ahead and replace the arrows with lines and let's see if that gives us something to work with. So we have one here, and well, this was an alkene, so now we make it an alkyne. And then I draw the other stuff on it. And do you think this would work as a possible synthesis? Like, would you agree that that's the correct starting material? You don't know. Okay, so let's draw the mechanism again and see if it would give us the correct product. You'd say yes. Okay, so I just draw that reaction again. And let's see what the product would be. So new bond over here, you lose a bond on the alkyne. New bond over here, and then new bond over here. So yeah, I think that would be a proper synthesis. No problem. So it is 8, but I will stay if you guys want to do anything else. So was there anything else from the review packet that you wanted? Number 1. Okay. So in number one, I first stared at it for a while and tried to figure out what the point of the question was. So it was asking for the pattern of reactivity, and I saw that these two were X'd out. So I was like, okay, why are they X'd out? So then I saw that there were a bunch of like hexagons on this side, and then there's also a bunch of hexagons here. So I matched them up and labeled everything. So this would be, oh, I should have erased that. Okay. So this is molecule B. This is A, C, A, B, C. And then on the right side, I saw that the first one with the X is A, the second one with the X is also A, the rest are B and C. That was step one. And then I was like, okay, cool. The only products with an X on it, the only reaction that didn't happen was an electrophilic substitution of molecule A. So then I looked at what carbon or what atom you're wanting to add the electrophile onto. So in the reaction, you have this electrophile and it's going on this position of the ring. And for A, it's going on that nitrogen. So I'm like, okay, why wouldn't it go on that specific nitrogen of molecule A? So then I go back to the electrostatic potential maps, and then I look at all the pretty colors. So I'm looking specifically at molecule A, and even more specifically, I'm looking at that one nitrogen that we couldn't add anything onto. So then you look at the electrostatic maps and see why couldn't you add anything onto it? So you know that for electrophilic aromatic substitution, you're reacting an electrophile with an aromatic ring. So in this case, the electrophile is electron poor, and the ring, to be more reactive, you want it to be more electron dense. If it's not electron dense enough, it's going to be fairly unreactive, right? So then I saw the pretty colors, and I was like, for molecule A, all the electron density, the red stuff, is concentrated in the center. And that one specific nitrogen up there is very blue. The blue means you have less electron density. So it's all being pulled towards the center. And then this nitrogen atom is like extremely electron poor. So it's a 2 electron poor, it can't undergo an electrophilic substitution. Okay, I'm not gonna lie, I don't know what the numbers are, so I didn't use them, but I'm assuming that the lower the number is, the less electron dense it is. Just because this is negative and this is positive, and then the one that was negative didn't get anything added to it. All right, was there anything else? You're welcome. Okay, well, good luck, guys. I know you're probably gonna do really well. The exam shouldn't be too bad, and just good luck.